students, welcome back to the JEE Last Mile Preparation Series 13. Today we will take up questions 25 and 26. But before I do that, by now you already know that I'm Sujata from CBSE NEET JEE Chemistry.in, and we are bringing you 2 questions every day until April 4th to help students get that extra edge for their JEE chemistry exam preparation. To keep me motivated in this task, please hit the like button and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. Let's get started. We continue with physical chemistry, and today we will take up 2 questions from the chapter Chemical Kinetics that you have learned in class 12. So here is question number 5. Okay, so let's first make ourselves familiar with this question. Let's read the question. For the reaction between C3H7I and aqueous sodium hydroxide, the following are the measurements of the rate of reaction at varying concentrations of the reactants. So you notice that in experiment 1, these are the concentrations of the 2 reactants and this is the rate of the reaction. Now the units of concentrations are moles per liter, and the unit for the rate would be concentration by time. So moles per liter per minute. Okay. Similarly, in experiment 2, these are the concentrations and this is the rate. And in experiment 3, these are the concentrations and this is the rate. Okay. You need to determine or deduce the rate law. 4 options have been listed here. We have to choose the correct option amongst these 4 options. So this type of question will be seen in section A of your exam paper. All right. So let's see how to start with the solution of these type of questions. First, let's write down a hypothetical rate law. Now, what do I mean by a hypothetical rate law? A rate law, an expression in which we don't know the orders of the respective reactants. So, concentration of C3H7I to the power of X and into the concentration of OH minus to the power of Y. X is the order of the reaction with respect to the reactant C3H7I. Y is the order of the reaction with respect to the reactant OH minus. The overall order of this reaction will be X plus Y. You are aware of that. Okay. So our task is to find out X and Y. Substitute it here. That gives us the rate law expression. All right. Let's go back to the table. Now in this table, we notice that the concentration of OH minus is maintained a constant in experiments 1 and 3, because of which we can easily find out X, the order of the reaction with respect to C3H7I. Okay, so let's first find out the order of the reaction with respect to C3H7I. Let's get the value of X. Then we can find out the value of Y. Okay, so to find out the value of X, we plug in these values in the hypothetical rate law that we have written. So we are going to choose experiments 3 and 1. Correct? We choose experiments 3 and 1 mainly because the concentration of OH minus is a constant. Okay, which means OH minus is not going to interfere with our deduction of the order of the reaction with respect to C3H7I. Okay, now before we write down the formula, let's also look into the rates of experiments 1 and 3. The experiment 3 has a higher rate, 9.2 into 10 to the power of minus 4. So we'll start with experiment 3. In other words, we will do experiment 3 divided by experiment 1. Okay, what do I mean by this? We plug in the values of rate, these concentrations in experiment 3 divided by plugging in all those values of experiment 1. Okay, so let's start. We start with the rate of experiment 3. What was that? 9.2 into 10 to the power of minus 4 is equal to the rate constant K into, what is the concentration of C3H7I? 0.15, right? 0.15 to the power of X into the concentration of OH minus in experiment 3 is 0.10 to the power of Y. All right. Now, what is the rate of the reaction in experiment 1? In experiment 1, the rate is 3.1 into 10 to the power of minus 4. That is equal to K into the concentration of C3H7I in experiment 1 is 0.05 to the power of X. This is a constant to the 0.10 to the power of Y. We are dividing these two equations. Okay, K gets cancelled. 10 to the power of minus 4 gets cancelled. These get cancelled. So what do we have here now? 9.2 by 31. 92 by 31 is almost, okay, we'll see about that. And this is 5 threes are 15, right? So 3 to the power of X. 0.15 by 0.05 is 3 to the power of X. Now this is almost 3. 31 threes are 91, so 3 point something. So we can take it as 3 or 3 to the power of 1. So the bases are the same. So what is X equal to? 1. So it is first order with respect to the reactant C3H7I. Okay. Now let's find out the order with respect to OH minus. Now that is not an easy task because we first look out for two experiments where C3H7I is a constant. We are trying to find out why, which is the order with respect to OH minus. So we don't want C3H7I to interfere. We want that to be a constant. But you notice that in all the three experiments, the concentrations of C3H7I vary. They're not a constant. So what should we do? We definitely cannot choose experiments 1 and 3 because in 1 and 3, the concentrations of OH minus is a constant. It gets cancelled and we will not be able to get the value of Y. So we have to choose either experiments 1 and 2 or 2 and 3, okay, where the concentrations of OH minus change. Let's choose experiments 1 and 2 and do the same process that we did to find out X, okay. So let's get started there. So let's choose experiments 1 and 2. Okay. Now what do? We identify which has a higher rate. We notice that experiment 2 has a higher rate. 1.3 into 10 to the power of minus 3 is equal to K into the concentration of C3H7I in experiment 2 is 0.10 to the power of X. We know what X is, equal to 1 into the concentration of OH minus in experiment 2 is 0.20 to the power of Y. Now, the rate of the reaction in experiment 1 is 3.1 into 10 to the power of minus 4. 3.1 into 10 to the power of minus 4 is equal to K into the concentration of C3H7I in experiment 1 is 0.05 to the power of 1 and this is 0.10 to the power of Y. Now we divide these two equations. K gets cancelled. Okay. Now what do? Let this be 1.3. This if you solve, you will get 130 by 31. Okay. That is equal to, this is 2 to the power of 1 into 2 to the power of Y. Now 31 fours are close to 130. So we get 4 is equal to 2 to the power of 1 into 2 to the power of Y. 4 is nothing but 2 square. That is equal to 2 to the power of 1 into 2 to the power of Y. So the bases are the same. So what is Y equal to? Y will be equal to 1. Correct? 2 minus 1. Y is equal to 1. So the order with respect to OH minus is also first order, right, with OH minus. So now what is the final rate law expression? Rate is equal to K into concentration of C3H7I to the power of X, which is 1, into OH minus concentration to the power of Y, which is also 1. You don't have to show 1 in the rate law. So what is the correct option? The correct option would be option A, where both the orders are 1. And the overall order of this reaction would be 1 plus 1, 2. And therefore, this would be a second order reaction. Okay, so that is about question number 25. Now let's move on to question number 26. Simple question. We have a hypothetical equation here, R, a reactant giving you products. The above reaction follows first order kinetics. So it's a first order reaction. Overall reaction is first order. In 40 minutes, the concentration of R changes from 0.1 molar to 0.025 molar. So this is the initial concentration of R, okay, R0. And this is the concentration of R at a specific time. At what time? At 40 minutes. So let's call this as R0. Okay. R at 0 minute, 0 time, which is 0.1 molar. And this is after 40 minutes, 0.025 molar. Then the rate of the reaction when the concentration of R is 0.01 molar is quite a straightforward question, but the calculation involves a few steps. Okay, so let's see what should we first find out. With the moment they say it's a first order kinetics, we should immediately think about this equation. K is equal to 2.303 by T log of initial concentration divided by concentration at time T. Okay, you are given all the information. You know the time is 40 minutes, you know the initial concentration, you know the concentration at 40 minutes of the reactant. The only unknown factor is K. Let's first find out K. Okay, so that is equal to, let's substitute all the information conveyed in the question. 40 minutes log of 0.1 by 0.025. You know that 0.1 by 0.025 is 4, right? 100 by 25. So that is 2.303 by 40 is into log 4, which is 2.303 by 40 is into 0.6020. That is the value for log 4. It's a simple value to remember. And if you substitute for this, you will get the answer as 0.347 or 0.35. Okay, it's a first order reaction. So what will be the value of the rate constant? Rate constant is K. Oh, this is 0.035. Sorry, it's 2.2 into 0.6 is approximately 1.2 by 40 will be 0.03, approximately 0.035. Okay, yeah. And what is the unit of the rate constant? I'll give you a shortcut formula to find out the unit of K. Now this is the first order reaction. All right. So unit of K is given as mole per liter to the power of 1 minus n per second or per time. Here the time is per minute. All right. So here, what does n stand for? N stands for the overall order of the reaction. And here it's a first order reaction. So moles per liter to the power of 0 per minute. So what is the unit of the rate constant for a first order reaction? Per minute. So this is the value of the rate constant K. But the question is to find out the rate of the reaction. The rate of the reaction when the concentration of R is 0.01 molar. So once we know it is a first order reaction, the rate constant value is going to remain as a constant. So we know the rate constant also. So now we have to use those information in to find out the value of the rate of the reaction. For that, we will make use of the rate law. Rate is equal to rate law expression for a first order reaction, K into concentration of R to the power of 1, because it is a first order reaction. K we found out as approximately 0.035 into what is the concentration of the react of R? 0.01 to the power of 1. So this will be 0.00, so 1, 2, 3, 4, 5. 0.003035 or 3.5 into 10 to the power of minus 4. 3.5 into 10 to the power of minus 4 moles per liter, per minute, or this moles per liter is given in terms of molarity. M per minute will be the unit of the rate or the value of rate. All right. So now let's get back to the question. Now here it is a numerical value type question which is likely to appear in your section B of your exam paper. So the answer is 3.5 into 10 to the power of minus 4. Okay, moles per liter per minute, or capital M, molarity, molar per minute. Okay, so that will be the unit of the rate, the value of rate, and 3.5 into 10 to the power of minus 4. So these were two different kinds of questions. There are many more concepts involved in the topic chemical kinetics. If you have liked today's video, please hit the like button and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. See you tomorrow.